Hey guys, welcome. Here is the video for your next set of notes, properties of exponents. This should be somewhat familiar to you guys. You saw it back in Algebra 1. That was a few years ago, so I figured I'd make a whole new lesson on it just because we will be using these properties of exponents when we start to solve exponential equations or expressions, equations rather. So you kind of need to be comfortable with these before we can move on to logarithms and just generally solving for exponential, functions. So our opening exercise, well, I guess I take it back. Our essential question is, how do properties of exponents help in simplifying exponential expressions? So we're going to start with this opening exercise. We've talked about this in class when we were graphing our exponential functions. So anything to the 0 power is 1. So that's an easy one. 2 to the 0 is 1. 2 to the first power is just going to be 2. And then if I think about 2 to the 1/2, I know that 1/2 is somewhere between 0 and 1. So we can take an estimate as to what we think that might be. So maybe we said, if we look at this exponent and say, well, since it's in between 0 and 1, maybe the actual value of this expression is somewhere between 1 and 2. So maybe let's estimate it to be about 1.5. And again, this is just an estimate. We are guessing at this point. And then we'll come to the actual solution here in a second. So our first exercise really revolves around finding the answer to this question, if we're actually correct here or not. So if I were to graph this function, this is probably the third time we've graphed it, for every integer of x from -2 to 5, then we're going to plot the points and connect them for a smooth curve. So just like we had mentioned up in the opening exercise, anything to the 0 power is 1. 2 to the first is 2. And we recognize that with this base of 2, we're doubling all of our values. So 2 squared would then become 4. If I doubled that, I would get 8. If I doubled that, 16, 32. We also discovered when we were graphing them that going in reverse is really just halving them, right? So half of 1 is 1/2. Half of 1/2 is a fourth, etc. So we've got these values. We can go ahead and graph them. So this looks like it's counting by 4s. So we'll say 0 and then put a dot at 1. If we go over to 1, that'd put us up halfway to 2. 2 to 4. 3 over up here to 8. 4 over to 16. 5 up to 32. And then again going in reverse order, so -1 is going to take us all the way down to 1/2, and then just a little bit lower to a quarter. So again, remember that it gets super close to that x-axis, but it never quite touches it. So we can see our function kind of going up like this, a smooth curve. So my question to you is the point 664 on the graph? So if I were to continue this table on to say the 6th value, where would that put us? So if I continued on with my doubling 32, if I doubled that, I would get 64. So we could say that yes, 664 is on my graph. Even though my graph technically didn't go that high, we can infer that that's going to go up to that point. In the opening exercise, we estimated the value of 2 to the 1/2 power. So again, we were assuming that maybe it was around 1.5. Does the graph of the function f of x equals 2 to the x power justify your initial estimate? So if I were to look back at my graph and look at the point, or look to see when x is 1/2, that would be somewhere between these two values, right? Or sorry, between 0 and 1. So if I checked somewhere in here, or on my graph here between 0 and 1, if I looked at 1/2, this would take me somewhere in there. It's kind of hard to see because this graph is so small, so I did a close-up to the right. So the right shows a close-up view of f of x equals 2 to the x power. And so again, if we were to follow this 1/2 to figure out where it puts us, then I can line up this point with my y-axis, and we can see now that it's a little bit closer that that y value is just a little bit below that 1.5 that I was estimating it would be at. So does it appear that 2 to the 1/2 power is halfway between 0 and 1? Almost, but it's a little lower. Or maybe we can say a little bit less than 1.5, like we guessed. So if we were to use this new graph now to estimate the value of 2 to the 1/2 power, if I counted my little grids here, it looks like it's counting by tenths. So this would be like 1.1, 1.2, 1.3, 1.4, and 1.5. So we can guess that maybe 2 to the 1/2 power is approximately equal to 1.4 instead of 1.5. So now getting a little bit deeper into the concepts, really fractional exponents denote some sort of root. So if we were to let a and b be numbers and n be a positive integer, then if b is equal to a to the nth power, a is an nth root of b. And so really what I mean by this sentence here is that if we were to imagine, say that this b was a 9, right? And this a was 3. Well, I know that 3 squared is 9. So if I look at this example in particular, then it says that a is an nth root. So the way that I would read this is that this 3 is a square root of b. So in this case of 9. 3 is the square root of 9. You can think of it with different examples. So say that I had done a 4 here. I know that the square root of 4 is 2. 2 squared equals 4. So this is a true statement, just like the purple one was. And again, if I read it the way that this states it, then 2 is the square root of 4, right? We can do this with different exponents too, so we don't just have to do square roots. So for example, if I did 2 to the third, that would be 2 times 2 times 2, which gives me 8. So again, if I read this the way that the sentence says it, 2 is the nth root, or the cubed root. 2 is the cubed root of 8, right? So this is just a different way of thinking about roots, actually. And you guys finished out last semester with radicals and properties of radicals and how to simplify them. So just like we mentioned here, if n is 2 or if my exponent is 2, then the root is called a square root. And that's not anything new to you guys. If n is 3 or if this exponent is 3, then it is called a cube root. Again, nothing new for us here. Just a new way to look at the same concept we're familiar with. So if we were to look at radicals like we are used to, and n is a positive integer, then we can look at this a couple different ways. So since these are the same root or the same radical, we could combine this to be in the same nth root, but we can combine a times b. So we'd have a times b, the nth root of a times b. Or if I think about it in terms of fractions and exponents, we could say something like a times b, or ab, is being raised to the 1 over n power. It's the nth root. So again, thinking back up here to our example, 2 to the 1/2 power is really the same as taking the square root of 2. And so the square root of 2, if you did put that into the calculator, I guess it just looks like this. If you were to do that, you would get approximately 1.4, which kind of goes along with our graph. So if I looked at this would be a similar thing. I could separate this to be the nth root of a divided by the nth root of b, right? Either way, we can combine and separate these because they have the same root. So if we go on to example 1, what is the cube root of 125? So we've learned this to be the cube root of 125. And when we were talking about this last semester, we were thinking, how could I factor this 125 to have 3 of the same number? So if we think back on our factors, 125 is 5 times 25. And I can keep that under the cube root. I can split up this 25 or factor it a little bit more. So I'll carry down the 5 that was there to begin with, times 25 is another 5 times 5. And then looking at this, I have 3 5s in here. So if I'm taking this cube root, I'm looking at 3 of the same number. So in our case, my answer would be 5. 5 is the cubed root of 125. Looking at the next one, I'm going to look at this one a little bit differently with our new properties over here with these fractions as our exponents. And so if I asked for the 4th root of 16, that would look something like this, the 4th root of 16. But what if I wrote it to you a little bit differently, or wrote it a little bit differently? So I could look at this as being 16 to the 1/4 power, because this is a 4th root, right? And so thinking about it this way, I think will be helpful for us in the future, because I can look at this as saying, this is the same as saying 16 to the 1/2 power raised to another 1/2 power. And so there's a little reminder of our properties of exponents on the back of this paper. But really, if you think about it this way, 1/2 raised to the 1/2 power would mean that I'm multiplying these two exponents to get this 1/4. So these are equivalent to each other. I'm just writing them a little bit differently. So doing it this way, I find to be helpful, because now I can easily take the square root of 16. The square root of 16 is just 4. So this now becomes 4. I still have it raised to the 1/2 power on the outside. And so again, the 1/2 power implies that I'm taking a square root. So the square root of 4 is just 2. So really the 4th root of 16 is just 2. So there's another example there. If we tried the 5th root of 100,000, again, 5th root would have that little 5 out front. 100, 1, 2, 3. And so looking at that one, if I thought about it the same way with those fractions, I could say that 100,000 is really the same as 10 to the 5th power. And so the way that I think of that one is, if I had 10, I would have a decimal place here, and if I moved it over 5 other times, 1, 2, 3, 4, sorry, I miscounted that. 10 to the 1st power would be 10, so that would be 1, 2, 3, 4, 5. Okay, so anyway, that's how I think of that one. And so again, this 5th root would mean that I'm taking it to the 1/5 power. Thinking back on our properties of exponents, if I were to multiply 5 times 1/5, then that would give me just 1. So really, this simplifies to 10 to the 1st power, which is just 10. So a couple different ways to do the same problems that we've done in the past. Now we're going to shift gears to the back. Here's a really important table for you guys. If you have a highlighter, I would definitely recommend highlighting this because we are going to see these properties of exponents probably for the next 2 or 3 lessons that I'll be doing with you. So this will help us solve exponential functions, and it'll also help us shift gears into logarithms, which are also very closely related. So looking at these, the properties we were just using on the front side were mainly these fractional exponents. Actually, I guess it doesn't really have examples of fractional exponents, which is why I put that on there. But we'll deal a little bit with negatives on this side of the page. But become comfortable with these if you're not comfortable with them already, because you'll see them again for the next couple of weeks. So if 2 to the 1/2 power is the square root of 2, and 2 to the 1/3 power is the cubed root of 2, then how would you write 2 to the 3/4 power? And so in this case, again, I would write 2 to the 3/4. Let me change that 4. 2 to the 3/4 could be written as 2 to the 1/4 raised to the 3rd power, because I know I can multiply those exponents to get this one again. And so if I were to write that in radical form, that would tell me that this is a 4th root. So 4 would go outside on my radical. It would be the index of my radical. And then this exponent would be what I've got inside here. Or I guess I take that back. If I were to write that, since this exponent is outside, I would say the 4th root of 2 cubed. You could also look at it differently though. So you could take this whole first expression and rewrite it as 2 cubed to the 1/4 power, right? Because you could still multiply those and get this fraction. So I'm really just writing it with these two swapped. And that way you could say that this is 2 cubed with that 4th root on the outside, which is what I was going to write initially. So either one of these would be acceptable ways to write or to rewrite this in radical form. So now we'll go into a little bit more with the fractions and negatives. So for any positive integer m and n and any non-zero number b, so my base is not a negative number, or not a 0 rather, then we can define b to the negative mn as a couple different things. So we could say that this is, looking back at these properties, if I have a negative exponent, I can write it as a reciprocal of itself and change that to a positive. So this could be written as 1 over b to the m over n. Or equivalently, if you were to look at this and write it maybe in radical form, you could say something like 1 over b to the m power, but the nth root of that. So that's another way to look at that. And so we're going to work through a couple of these problems with these properties, but not using any variables necessarily, just simplifying them as numbers without radicals or exponents. So looking at this one, for example, I could just write 1 over 4 to the 3/2. So notice that 3/2 becomes positive now. Another way that I could think of this is saying that I have 1 over 4 to the 1/2 cubed. So again, thinking that I could multiply those to get 3/2. The reason I did this is because the 1/2 power again means that I'm taking a square root. So the square root of 4 is 2. So I could write this as 1 over 2 cubed. And 2 cubed really means it's 2 times itself. 3 times. So 2 times 2 times 2 is 8. So this in turn simplifies to just 1/8. Notice it doesn't have any negatives, no radicals, no exponents, nothing. So that's the idea behind these, and you'll get a few problems like this to work on your own. This one, same process, except it's negative 2/3 instead of negative 3/2, but let's do a similar thing. So I'm going to put the reciprocal, 27 2/3. This one I'm going to rewrite as being 1 over 27 to the 1/3 power squared. And so 27 to the 1/3 means that I'm taking a cube root. A cubed root of 27 is just 3. So 3 times 3 times 3 gives me that 27. But I still have that raised to the 2nd power because that I didn't account for yet. And so 3 squared is 9. So this whole expression really just simplifies to 1/9. This one will be an easy one. The 1/2 we already know is the square root, so this one I would write again the reciprocal, so 4 to the 1/2 power, meaning that I'm taking the square root of 4, so 1 over 2. The square root of 4 is just 2. This here, since the 7s are the bases, so it's 7 to the 1/2 power times 7 to the 1/2 power, thinking back on these properties of exponents that are right above, if I have two things with the same base, like A and A, all I have to do is keep that same base and add those exponents to each other. So in this case, I would have 7 to the 1/2 plus 1/2, which really becomes 7 to the 1st power, or just 7. So that's an easy one. This one's also pretty easy. I have 3 of the same things, so the way that I would think of it is I've got 3 to the 1/3 powers cubed, because I've got 3 of those expressions. Thinking back again on those exponents, I can multiply the exponent raised to the next power, so 1/3 times 3 is just 1, meaning that this simplifies to just 3. This next one, I would probably recommend multiplying these exponents right off the bat. So you've got 64 raised to the 1/6 power, 3 times 2. And so here this is saying that you're taking a 6th root of 64. So 6th root of 64. And this is where I would start to factor out. So I know, I guess I'm going to factor it out to the right just so I have a little bit more room here. So 64 is the same as saying 32 times 2. I could factor that 32 to be 16 times 2 and carry down this 2. 16 is 4 times 4, carry down both of those 2's. And then 4 is 2 times 2. This one is also 2 times 2, and then 2 more 2's. So really I have a total of 6 2's that I could write in here. So the 6th root of all those 2's, 2 times 2 times 2 times 2 times 2 times 2, really leaves me with just 2 as my answer, because I've found 6 of the same number here. So again, you guys will get a little bit of practice with this. And then once we're comfortable with this, we can move on to solving exponential functions. Example 3, we're doing the same process, except now instead of just using numbers, we are using some of our variables. So I will do the first 3 here for you, and then I'll have you do the last 3 as parts of your exercises. So I'll be checking those in a notebook check. So this, those have the same base, so I can rewrite this as the same base but add those exponents, so 1/4 plus 1/4. And so that would give me 2/4. So this equals b to the 2/4, which is really the same as saying 1/2. And it says to write each expression in this form. So we've already got it in that form. So that's how I would leave my answer. This one, I'll let you try this one as one of your exercises. I think I meant to leave these bottom ones, but I'll kind of mix them up for you. So this one's pretty similar to that first one. This next one is almost similar, except the fact that you have different denominators. So here, since we have the same base, I would keep that base of b, but now I've got 1/5 plus 3/4. And so in this example, we'd have to find a common denominator, which I think would be 20. So thinking about 20, I could change this 5 to a 20 by multiplying by 4, but I'm going to do that in both the numerator and the denominator. On this side, I'd multiply by 5 over 5. And so now my base stays the same. My base is still b, but my fractions now are going to become 4 times 1 in the numerator, which is 4. And then this would be 20. Up here, 3 times 5 is 15, denominator 20. And so now I can combine those to be a base of b, and then 4 plus 15 would be 19/20. So that's how I would leave my final answer there. So I'll let you try this next one. Similar concept, finding a common denominator. This next one is really simple, and so all we're doing is multiplying those exponents. So I would have b to the numerators, it's 1 times 2, which is 2. Denominator is 5 times 3, so 15. And that's how I would leave that one. And then this next one, again, they have the same base, so I would keep that base of 64. 1/3 and 3/2, I could then just add those fractions to each other. So 1/3 plus 3/2. And so in this case, we'd have to find a common denominator, which should be 6. So to change this to a 6, I'd multiply by 2 over 2. To change this to a 6, I'd multiply by 3 over 3. And then let's see what that gives us. So I've got 64 now raised to the 2/6 plus the 9/6. So 9, 10, 11, 11/6 is what we get for that exponent. And so we had already figured out 64 to the 1/6 power. We had solved that, and we said that that was 2. So let's use that to help us here. So this I'm going to rewrite as 64 to the 1/6 power raised to the 11th power. And so again, earlier we said that this was really equal to just 2. So 2 to the 11th is what my answer would be here. And I'm not going to take the time to multiply that. That'll be a pretty large number. But 2 to the 11th power. So hopefully that made a little bit of sense to you guys. Finish these next 2 exercises just for your notebook check, just so I can see that you were practicing some of the stuff that I taught today. And then you've also got an assignment for some additional practice. I'll answer some questions when I see you all on Thursday. And then we'll start moving on to solving more complex exponential functions. So have a great rest of your afternoon. Please behave for the sub. Make sure you sign out if you go to the restroom on the iPad. Yeah, I will see you guys on Thursday.